Nuclear fusion is considered the holy grail of energy production and promises to be a potentially inexhaustible and climate-friendly energy source of the future. But the reality so far has been quite sobering. For decades, the mantra has been, "We will be ready in 30 years." Yet the breakthrough keeps getting pushed back. But that could now slowly be changing as major success news comes from Greifswald in Germany. The Wendelstein 7X at the Max Planck Institute sets a new world record in May 2025 for the so-called triple product. And the first commercial nuclear fusion power plant is getting closer and closer in the planning stages. But what does this world record really mean? Is this the final breakthrough or just another headline in the never-ending quest for research? And how close are we to the first commercial power plant? To find out, I also spoke with the expert Professor Dr. Klinger from the Max Planck Institute. So let's clear all that up now. And with that, welcome to the German Science Guy. My name is Dr. Jakob Botton, and in Germany we say Los geht's. For nearly 70 years now, research groups around the world have been working to harness nuclear fusion as an energy source. At Wendelstein 7X in Greifswald alone, a total of around 1.4 billion euros has been invested since 1995. And now things are getting even more serious. Germany wants to be at the forefront of the international race for nuclear fusion. And the goal is truly ambitious. The very first commercial fusion reactor is to be built here in Germany. And new breakthroughs and even a world record have been achieved at Wendelstein 7X as well. At the core of the Sun, hydrogen atoms fuse into helium at 15 million degrees and under unimaginable pressure. This releases a massive amount of energy, and researchers want to make that possible on Earth too. In short, what is nuclear fusion? The only problem is, normally atomic nuclei repel each other because they are positively charged, just like two same poles of a magnet. To overcome this repulsion, the nuclei need to be moving at extremely high speeds so that they can collide and then fuse. Motion and temperature are related. In other words, temperature means that the particles have more kinetic energy, so the hotter a substance is, the faster the particles move. And that means in turn that what we need is heat. But there's a small catch here, because we need about 100 million degrees Celsius. So really hot. Well, in any case, if we want to generate energy using a fusion reactor, a mixture of deuterium and tritium is heated to this temperature inside the reactors. In the case of Wendelstein 7X, deuterium has 1 proton and 1 neutron. Tritium has 1 proton and 2 neutrons. And when the nuclei fuse, helium is produced and a free neutron remains, which has a lot of energy. And this energy can be used in the form of heat, from which electricity can then be generated. And just to be clear here, although we are focusing today on the Wendelstein 7X Stellarator in Greifswald, there are a few other types. Many people are probably familiar with the tokamak, such as the ITER in France, or laser fusion. But today we are talking about a record, and this is why we talk about the Wendelstein 7X. In this reactor, the gas is heated using microwave radiation to bring it into a plasma state. That is a state in which the atoms break down into their constituent parts. The challenge now is that the plasma must not come into contact with the walls, because it cools down immediately, thereby losing energy and causing the reaction to stop right away. That's a standard problem with magnetic fusion. To counteract this, the Stellarator uses a very complex 3-dimensional calculated magnetic field generated by 50 coils. And pay close attention here, the Stellarator really only has outer coils, which is why the reactor needs this complex shape. Through this magnetic field, the plasma is stably confined and effectively floats in the air. This prevents it from reaching the walls and stopping the reaction. And now a major breakthrough has been achieved. In May 2025, during the OP 2.3 experimental campaign, a new world record was set for the so-called triple product. The triple product consists of plasma density, temperature, and energy confinement time, and is a key performance metric for a fusion reactor. If it exceeds a certain threshold, the reactor generates more energy than must be input in form of heating power. The fusion reaction then sustains itself without the need for further heating. And a new record has now been achieved. They succeeded in heating the plasma to up to 30 million degrees and maintaining this state stably for a full 43 seconds. This is the highest value measured to date for devices based on the Stellarator principle. The key point here is the Lawson criterion. If we manage to exceed this value, then the reactor generates more energy than it consumes for heating. And that is exactly what we've been waiting for and where we want to go. Otherwise, it will be difficult in the long run, because who wants a power plant that consumes energy instead of producing it? And for a fusion reactor using deuterium-tritium fuel, the target is around 3 × 10⁻21 per square meter kilo-electron volts. But achieving that isn't so easy for very simple reasons. I spoke with Professor Dr. Klinger from the Max Planck Institute about this.
The Wendelstein Stellarator couldn't possibly meet the Lawson criterion because its volume is too small. It simply can't reach the required temperature.
To do that, it would have to be built significantly larger. At the moment, the measurements taken are being used to estimate the performance of a larger reactor and then reassess whether that value can be achieved. And that was indeed the case.
That means they test it out on a small scale to keep costs down, and once they're sure it works, they can move on to the larger ones, which then requires a larger investment. So if with a smaller volume these temperatures are reached, if these necessary parameters are met with a smaller volume, then that points in the right direction. After all, you can always scale it up.
In other words, this success is definitely a big step in the right direction. This success was made possible by a collaboration with the Oak Ridge National Laboratory in the United States. They contributed a novel pellet injector. To keep the plasma stable, new fuel must be continuously supplied, and that is exactly what this injector does. It produces millimeter-thick frozen hydrogen rods. With that, during the record attempt, approximately 90 hydrogen ice pellets are then continuously fired precisely into the plasma through a blowpipe at a speed of between 300 and 800 meters per second. That actually sounds super simple, but of course it isn't. This is because the fusion plasma must be continuously fed without cooling down too much. If too much frozen hydrogen were injected at once, the reaction would stop. That's why researchers had to time it with extreme precision. And this was achieved using the pellets while powerful microwaves heated the plasma. It worked so well that a new world record was set. However, it didn't stop at just one milestone. During this test run, a new record was set not only for the triple product, but also for energy output. The previous record stood at 1.3 gigajoules in 2023, and that has now been increased to 1.8 gigajoules with a plasma duration of 360 seconds. And there was also a new record for the beta value. The beta value is an efficiency indicator and describes the ratio of plasma pressure to magnetic pressure. This means that the higher the beta value, the more fusion occurs for less energy input. Here, a value of 3% of the total volume was achieved for the first time. So this experiment was truly a success. The goal is to build on this success, and with that, the first commercial nuclear fusion reactor is set to be operational in Germany by 2045. Total costs are expected to amount to approximately 2 billion euros. The Made in Germany reactor is therefore a very hot topic here in my country.
Where the intuition tells you, well, now it doesn't need that much anymore. And that in turn has also led the investors to give it a try. That is, let's just put some money into it now and support startups like this. And they're now pushing even harder.
Which is of course very positive. The huge leaps in development and the enormous attention are now encouraging people to just take a chance. But it doesn't seem to be a lack of ambition that is holding us back. But there's still a list of critical factors that keep coming up. And of course we need to talk about these. And that's what we look at the big hurdle of this video. I have this part in every of my videos where we look at the problems of new innovations, and if you like that, feel free to subscribe and turn on the notifications so you don't miss any other videos and support this channel. By the way, thank you so much for over 100,000 people. I was really excited when I saw it. It was midnight here in Germany and I was watching the counter going up, and yeah, thank you so much guys, it really means a lot to me. Okay, let's step into the big hurdle. So we're hearing success stories about new world records in fusion research almost regularly now. And they always sound incredibly spectacular. But we have to be honest, it always, or at least most of the time, sounds more impressive than it actually is in practice. Because the biggest problem with nuclear fusion remains that to date, no reactor worldwide, not even Wendelstein 7X, is capable of generating more energy than is put into it for heating and magnets. To change that, we would have to either massively scale up the power plants or drastically strengthen the magnetic fields. Both are extremely difficult to implement technically. ultimately it is also a market issue.
In the history of technology, it's not the case that the first ones, we're talking about first of a kind here, are used primarily to gain experience to build something like this, to see how well it runs, how reliable it is.
That means, do we wait for a perfect power plant, or do we settle for several plants that run only semi-well for now? And that brings us straight to the next sticking point: money. And when it comes to money, we're talking about very large sums. The Wendelstein 7X alone, as a purely experimental facility, has already cost around 1.4 billion euros, as I briefly mentioned at the beginning. According to estimates, future prototypes will cost billions of euros more, or even more. The International Research Reactor ITER, for example, is already estimated to cost over 20 billion euros, and this too is purely a research reactor. And on the top of the construction costs alone comes a mind-boggling complexity. After all, we're talking about a very special magnetic field and above all components that must withstand continuous operation at 100 million degrees. Whether the materials can handle that over the long term without needing constant replacement is also a huge question. And while we're on the subject of materials, I need to clear up a small misconception. Nuclear fusion promises to be a clean alternative, but unfortunately it isn't quite that clean. While it doesn't produce highly radioactive waste like nuclear fission does, radioactive waste is still generated. This is due to the neutrons released during fission. They collide with the steel structures of the reactor walls and activate them. The material itself becomes radioactive by that.
But you don't have to wait 10,000 years, just around 100 years. That still sounds bad, but that's a perceptible time frame and it's quite manageable.
But I have to say, sure, it's a shorter process, but the radioactive waste is still there. Above all, we're talking about thousands of tons of steel here that will become radioactive and will also have to be stored somewhere for at least 100 years. That's a huge space and cost factor that we definitely shouldn't underestimate. Given all the challenges and the current state of research, the question eventually arises as to whether this is even economically viable, because that is another misconception I keep encountering. I followed up on this with Mr. Klinger. He said that the price would have to be in line with renewable energy to be competitive. However, since fusion power plants would provide highly reliable energy, meaning they would always be running, especially when there's no wind, the price will likely end up being somewhat higher.
That also depends on technological factors. How affordable can you get such large components, like the magnets, for example? That's the most expensive and complex component. The cheaper the production and cost of the magnets become, the cheaper the electricity will be, but I can't say exactly yet where we'll end up overall.
For nuclear fusion to be truly competitive after 2040, however, those costs would need to be around $80 to $100 per megawatt hour, or even lower. However, this will be very difficult to achieve for early fusion concepts, regardless of whether they are small or large. By comparison, the levelized cost of electricity for ground-mounted photovoltaic plants coming online in 2025 is around 7.2 to 7.6 cents per kilowatt hour. That corresponds to about 72 to 76 euros per megawatt hour. While this depends on the size, it gives us a rough idea of the price differences. Nevertheless, according to Mr. Klinger, nuclear fusion could play an important role in our grid, especially in metropolitan areas. There, the power plants could be used for supply energy continuously without having to transport it over vast distances. A mix of renewables and stable large-scale power plants would likely be the optimal compromise. Let's see if that works out. And before we now wrap up today's big hurdle, let's turn to what is perhaps the greatest challenge: breeding tritium. Tritium is the actual fuel, but it occurs only rarely in nature. That's why the reactor must first produce its own fuel. This happens in the blanket, a layer in the reactor wall, and lithium is embedded in the band structure. When the neutrons from the fusion reaction strike this lithium, tritium is produced. This happens in the blanket, a layer in the reactor wall, and lithium is embedded in the band structure. When the neutrons from the fusion reaction strike this lithium, tritium is produced. So through the interactions between lithium and the neutrons, tritium, the reactor's actual fuel, is created. This is a massive hurdle, keeping the cycle stable despite all the other stresses. But since lithium is a stable element and tritium is not, this is currently the only way. Okay, what can we say in the end? The new world record set by Wendelstein 7X is without question a technical masterpiece and proves that the Stellarator can indeed hold its own against a large tokamaks. But yes, the big hurdle is quite significant today, because the energy balance, the gigantic costs, the material costs and all other factors are truly massive. Personally, I'm nevertheless firmly convinced that research in this area is worthwhile, on the one hand because we may one day be able to use the technology effectively for energy production, but also because we never know what other groundbreaking innovations might come out of such research. That's also my take on laser nuclear fusion. If we really manage to create such small ultra-powerful lasers, it could become very valuable in entirely different fields, such as material research or even medicine. So I think it's very important to research on that, producing energy with it. To be honest, maybe this is 30 years away. But what is your opinion on that? Please write it in the comments, and thank you all for all the comments under my videos. And here you find another video of this channel. Take a look, and I say Auf Wiedersehen, which means goodbye in German. Your Jacob.